Hello everyone, I am very pleased to present you today a study on a new structural dynamics modification strategy based on expanded Squeal operational deflection shapes. So to begin with, I would like to briefly summarize the tools that are classically used to analyze Squeal issues. To characterize the Squeal experimentally, the brake system is mounted on a dyno test bench, and braking parameters such as pressure, temperature, or velocity are defined to reproduce the squeal. Measurements are then performed and an operational deflection shape, or ODS, characterizing the squeal limit cycle is obtained. The animation here on the right shows the ODS that will be used as illustration for this presentation. The major interest of such measurement is that it captures the real behavior of the squealing brake, but it is very difficult to propose countermeasures directly from it because of the quite low spatial density of sensors. To work directly on test data, we could think of the historical structural dynamics modification techniques, called SDM techniques, which allow to add mass, springs, or dampers at sensor locations. But these techniques need scaled modes, which is not available with ODS, and it is difficult to translate the local modifications at sensors to physical modifications of the real brake system. The squeal can also be analyzed numerically. The finite element method is the most widely used technique, and it gives access to fine geometric details and continuous field over the whole system. The standard process, called the complex eigenvalue analysis, consists in first applying a static brake pressure, then linearizing the model around this static state, and finally computing the complex mode. Some of these modes may have negative damping, and the huge interest of the numerical analysis is that we can easily simulate the impact of any system modification. The typical strategy is to separate modal frequencies to avoid interactions involved in squeal. But one major difficulty is that the model predictions will be relevant only if the model is representative enough of the real brake system. The test versus FEM correlation must thus be checked. To do so, the experimental ODS and numerical mode shapes are compared. With the topology correlation here, the test wireframe is superposed to the FEM mesh to observe the numerical shapes at sensors. The animation shows in blue the observation of one particular FEM mode, and in red the ODS. The correlation between the two shapes visually seems unsatisfying, which is confirmed by the modal assurance criterion. All the numerical modes from 3 to 5 kHz are compared here with the single ODS, but the best correlation only reached 20%. This bad correlation can be due to the test site, because the ODS characterizes a limit cycle containing nonlinearities, which is not, strictly speaking, a mode shape, and because obviously experimental issues such as noise, setup problems are always present. But most of the time, the bad correlation also arises from the model side because it is not representative enough of the true system dynamics. So to use the model alone to propose further system modifications, model updating is thus necessary, despite high cost, time, and absence of guarantee on the results. The strategy developed in this presentation proposes to combine both the experimental and the numerical data to overcome these limitations. The proposed strategy can be divided in 3 steps. First, the ODS is combined with the model using an expansion strategy. Then the resulting expanded shape is scaled to further perform structural dynamics modification techniques. And finally, a new thickness SDM strategy is used to separate frequencies of interacting modes with the objective to reduce the squeal. So let's begin now with the first step, which is the expansion of the ODS. The objective of expansion is to estimate the ODS at all model degrees of freedoms. To find the best estimate, we need to define 2 error criteria. The first criterion is the test error, which evaluates the gap between the expanded shape motion and the ODS motion. The second criterion is the model error, which tends to measure the amount of force that must be applied in the model to obtain the expanded shape. So you can see here 3 expanded shape candidates that will be used to introduce the 2 criteria. To measure the test error, the first step is to observe the expanded shape from the point of view of the sensors used for the measurement. This observation is animated in blue, while the red wireframe corresponds to the ODS. The second step is to compute the gap between the ODS and the model shape observation. This gap is displayed at the bottom for the 3 expanded shape candidates, and the test error is simply the Euclidean norm of the gap. For the first shape, which does not follow at all the measurement, the relative gap is very high, with a relative test error of 95%. For the second shape, the correlation seems very good, and the gap animation shows almost only noise. The relative test error is low at 14%. And finally, the third shape exactly corresponds to the measurement at sensor location. So the relative test error is exactly 0%. The second criterion is the modeling error. The model dynamics never corresponds exactly to the real system, and to compensate that, residual loads must be applied in the model to obtain the expanded shape. To measure the amount of residual loads, we first evaluate the static displacement they generate, and then we compute the associated strain energy. The modeling error corresponds to the total strain energy generated by the residual loads. For the first shape, with very small motion, few residual loads are applied and the model error is about 0%. For the second shape, a little more residual loads are applied, but they represent only 3% of model errors, and the resulting motion is way closer to the measurement. Finally, for the third shape, too high residual loads are applied, resulting in a model error of 82% and a concentration of model error at the sensor locations. To find an optimal shape, both the test and the modeling error should be minimized. To do so, we classically build a multi-objective cost function in which we introduce the parameter gamma to balance between the 2 errors. To each value of gamma corresponds an optimal expanded shape associated with 2 values of modeling and test errors. The graph here shows the evolution of both errors with the gamma parameter. The relative error of test is in blue here, and the relative error of model is in red. For very low values of gamma, the cost function reduces to the minimization of the modeling error only, and this is easily achieved by applying practically no residual loads in the model, and the expanded shape shows almost no motion, as you can see here. When gamma increases, the expanded shape gets closer and closer to the measurement. The test error decreases up to almost only noise, and the modeling error only slightly increases. If we continue to increase gamma, we start to compensate for the test noise with the modeling error, which leads to the concentration of residual loads at sensors, and the strain field of the expanded shape is clearly not physical anymore. To conclude, the best choice of gamma corresponds to the lowest test error and just before the modeling error starts to concentrate at sensors. With this choice, we get an expanded shape close to the measurement and with a smooth and physically representative strain field, which is mandatory to perform the SDM. But before, SDM also requires to build a model from the expanded shape. This is the second step of the procedure. The complex shape we just obtained is composed by two underlying real shapes, and to be able to further quantify the impact of modifications, these shapes must be scaled. Mode scaling is what encodes the amplitude of the mode shape motion in response to a known force. In this case, the two shapes come from an ODS where the input force is not measured, so the only data available for scaling is the model. To do so, the nominal model is first reduced on the expansion subspace, which leads to two real modes and their associated frequencies. Because the model dynamics is a bit violated during the expansion procedure, the frequencies are higher than expected, and this is corrected by imposing the exact expansion frequency to these two real shapes in the model. We now have a model with two modes at the exact squeal frequency, and the final objective is to separate them in order to reduce the squeal occurrence using SDM strategy. SDM techniques are based on the sensitivity analysis of model frequencies to a system modification. It can be shown that the model frequency evolution is directly related to the evolution of strain and kinetic energy resulting from the system modification. For instance, if a modification adds more strain energy than kinetic energy to a specific mode shape, its model frequency will increase. Contrary to the historical SDM strategies, which focused on local modifications at sensors, our model is now defined at model degrees of freedoms. This allows us to test physical modifications like an increase or decrease of thickness at the surface of some parts of the system. To determine areas where thickness modification has the strongest impact on model frequencies, the first modification is to add a thin and uniform thickness layer. We show here on the caliper and the bracket how it is built. The map of normals to the surface is used to extrude the thin material layer. To estimate the unknown motion of the new nodes in the layer, a dynamic expansion is performed by imposing the mode shape motion at the model frequency. The animation here shows the result of the motion estimation in the whole layer. Now that the motion in the whole thickness layer is known, we can compute the strain and kinetic energy density. And using the sensitivity analysis explained before, we know that the difference between the two energies is directly related to the modal frequency shift. And this is why we have called this map the shift energy density map. So this map tells us that in red areas, where the strain energy is higher than the kinetic energy, adding material will increase the modal frequency. And of course, it is the opposite in blue areas, where adding material will decrease the modal frequency. With this tool, we can now tackle the final objective, which is to separate the two mode frequencies. The shift energy map is computed for the two mode shapes. Then we want to separate the modal frequencies, so the interesting map is the difference between the two, which is shown here. For instance, with this map, if we want to move the second mode frequency higher than the first mode frequency, this map tells us to add material in red areas and to remove material in blue areas. Of course, this map should then be corrected to respect engineering constraints, but for the sake of simplicity here, we apply this modification map directly and obtain the frequency evolution shown in the right. With no modification, both modes are at the squeal frequency, 4050 Hz, and the more we increase the modification amplitude, the more the frequency are moved apart, as expected. I would like now to conclude with an overview of the presented procedure. So from an ODS measurement of a squeal event and a finite element model, it is possible to estimate the ODS motion at all model degrees of freedom using expansion techniques, and even when the test-FEM correlation is not very satisfying. From the complex shape, a modal model is built, composed of two real modes at the squeal frequency. Then a shift energy map is generated, showing where to add or remove material to separate the modal frequencies. From this shift energy map, acceptable modifications taking into account engineering constraints are proposed, from which mode shift predictions are computed. And this ends my presentation. Thank you.